Thank you. Hi. So my talk is going to be about unsupervised learning of state representations for multiple tasks. So what's the motivation of that? So in many reinforcement learning tasks, usually the agent will have to solve multiple tasks in order to solve its goal. So for example, take an Atari game like Space Invaders. So the agent will have to figure out on its own in some way to shoot at its opponent, but also to find a way to avoid being shot himself and to avoid obstacles, or it might specialize in different parts of the state space. And the way we usually approach that is by learning a single policy, for example, using a deep queue network. And I call this multitask because it's actually has to figure out on its own what are the different tasks that it has to solve. But in a lifelong learning setting, we will want the agent to be able to solve multiple tasks and not just a single task, like for example this game of Space Invaders. So in the most trivial example, you will for example have to solve different games, different Atari games. And the way we usually approach this problem is that we give these games one by one and train a policy to solve each of these games. And so why do we actually do that? Because it's really difficult to train one single policy that solves all these tasks. And there is a variety of different problems. For example, you have the problem of catastrophic forgetting. So you might forget while playing Pong very important features that you've learned while playing Breakout. And the more different tasks you have, the harder it is to keep all the data of all these things in your memory to do experience replay, and therefore you forget and you unlearn what's really important for solving all of these tasks. And so this is really a spectrum of solutions, and I think we need both. So in the previous task, we had a good example of when you want to solve multiple tasks with one policy, because you also can then generalize better in the individual tasks. But there's been little work on really trying to give the agent some idea, some structure to tackle the problem of identifying by itself what are tasks that it should specialize on. And so in this work, we're really on the far right end of the spectrum, but as I said, we believe both of these things are very important. And so the goal of our work is to enable the agent to identify and solve multiple tasks in an unsupervised manner without telling the agent beforehand what are actually the tasks and how to solve them. Okay, so how are we going to approach that? So we're going to use basically an approach that's called state representation learning. And so before I tell you how this works for multiple tasks, let's just go through it for a single task. So the idea is here, instead of training directly on the observations, you first try to extract a low-dimensional state representation S. And you're doing this in an unsupervised fashion. So one way, for example, that you do is you use an autoencoder or other unsupervised things. And the good thing about doing this explicitly is that you can inject prior knowledge into the extraction of the state representation, and you're therefore more data efficient. So the approach we're going to use is by Rico, my colleague over there with the red curly hair waving its arm. It's called state representation learning with robotic priors. And in a nutshell, this approach tries to formalize a loss function that formalizes different aspects of what we believe, in a task general way, good state representations are. So for example, that in the different parts of the state space, your actions should have a kind of proportional effect and other things like that. Okay, so this is now how we would do it for a single task, but how do we extend this to multiple tasks? So the idea is to extend this architecture by training basically adding a task extractor network. So this is this part over here. And the idea is very simple. You just have another branch from your observation that maps on a discrete variable, a task. So for example, this could be a neural network with softmax outputs. And then the whole trick is that you're going to use the output of this thing to gate your state representation extraction. And so basically this is like a transistor, like a gating switching mechanism, and it's really implemented as a multiplicative weight on the weights of this function here. And also in the same way, you can use it to then select the policy. And importantly, so we're going to train this entire thing in a joint optimization manner, which has the benefit that the extraction of the state, so the prior we use there, can also help extract the different tasks and vice versa. And then because we have due to the ability to extract a very low dimensional state representation and to have low dimensional state representations for different tasks, we're then going to be able to very efficiently learn the different policies using standard methods. Okay, so this is somehow very much related to already very old work, like the mixture of experts, which was proposed by Jeff Hinton's group. And it is indeed, you can see it like that. Like we have different task-specific experts extract, like expert extractors of state representations and expert policies. Okay, so if we now apply these like two ideas and we try it out, unfortunately it doesn't work. So what happens in our case that the network was not able to kind of use this additional structure that we added of being able to extract tasks and using it to modulate the state representation. But instead it would still try to fit one state representation for all the tasks. So we thought, what other aspect of like the problem or in general of learning in such a lifelong setting can we exploit to make this possible? And we came up with the idea of task coherence. And this is a very simple idea that I want to briefly explain. So in a standard reinforcement learning setting, you have these traces of observation, action, rewards, and you do this over some time, and then you have different episodes where you run your learner. And one thing that is very unlikely is that by now I'm encoding the color, by the color I'm encoding the task, that you're going to switch the task at every time step. So you're not going to do one action in Space Invaders and then one action in Breakout. But rather you're probably going to have some kind of coherence over time over your tasks. So for example, you can assume that during an episode the task is very unlikely to change, but that when you switch to a new learning episode, then you're going to have a different task. And this is actually what we're trying to encode with another loss function. And so I'm not going to go into detail here, but the loss basically says something like this, that if you have two observations that are from the same episode, then we're going to minimize the cross entropy between the output of the task detector. And this is one part of the loss, and we tested different ways. Okay, so how does learning actually work? So we're considering a very simple example with slot car racing. So here in this example, the agent has to control either the red or the blue car, but it doesn't know beforehand about the task, or it doesn't even know how many tasks there are, and it needs to learn that by itself. And so we're going to get an observation. The task detector is going to say this is task 1, 2, 3, n, whatever. But in the beginning, it's going to be totally random. Then we have the state representation, which is also going to be random. And then also the policy is just, we're going to use a random policy to correct the data. And then once we've collected data, we run our learning. And we use our two priors, our two loss functions. So on one hand, the robotic prior loss to shape the state representation. And on the other hand, our task coherence loss to shape the task detection. And so what then comes out in the end? So we have different variants of our example. So the one that is the simplest one to understand, which is why I'm showing it here, that we just display the car that is currently controlled in the bottom left corner. And as I said, the agent doesn't know anything about this picture. It will have to figure out that the bottom left corner encodes the task, and that then it should extract kind of some information about the cars in order to solve the task of going around the track as fast as possible. And then what's going to happen, it's going to see the blue task, then it's going to find, oh, this is probably task 1. It's going to gate its state representation. It's going to learn, that's actually the result of our experiment. It's learned the circular structure of the slot car racing track. It's going to say, okay, I'm here. It's going to execute the policy. And then once we switch the task, it can switch to the different task detector, find the other state representation that it found for this task, and successfully execute the policy. So we did quite a lot of experiments with different variants of this task. We analyzed what the agent learns compared to different baselines. And yeah, the take-home message is you should really exploit the problem structure and try to formulate it in some way to put the structure into like a neural network to be more data efficient at learning. And if you want to know more about this, my poster is over there next to the door. Thank you.
I think we have time for 1 or 2 questions while the next speaker sets up.
So there's some graphs and stuff that you have on the poster that you didn't have in the presentation, but can you talk a little bit more about the ways that you guys evaluated how much some of these things helped? And then also, did you try any other ways of conditioning the policies like giving the task as an input instead of a multiplicative weight at the end and that kind of thing?
Yeah, very good question. So we actually tried different loss functions. So we kind of set the different losses we proposed to 0, and we really figured out that of the different loss functions that we were using this robotic prior loss and the task consistency loss, which I show were really the most important one. Without that, it wouldn't be able to learn the policy. And the second question was if we condition it, if we give the task beforehand, sure, then this was kind of a sanity check for us. If we give the task beforehand, would it be able to solve it? And because it was yes, we then kind of proceeded to the next step of trying to also enable the agent to automatically extract the task.
Yeah, I was asking more if you conditioned basically the policy network that you had, where instead of multiplicative on the higher level weights, you gave the task as a separate input to the state.
This you mean?
Yeah.
So you mean just like a numerical input as part of the state? Yeah. This this would also work, and this was also what we tested in the beginning. Yeah. But it's still a simpler case than as trying to detect it yourself, right?
Sure. I was just wondering if you guys did yours perform better? Was there a difference that you noticed?
No, not really a difference, because in this example it was able to perfectly extract the task from the image.
Thank you.
Thank you.